So in the last lecture, we looked at the velocity motion model, and so today we are going to look at the odometry motion model, right? So the odometry information is essentially information on how much the robot has moved, right? How much the position of the robot has changed, and the odometry data is typically obtained from looking at motion sensors that are there on the bot. Right, the most popular kind of motion sensor that we use is the wheel encoder. Right, so looking at these kinds of wheel encoder information, so on and so forth, you integrate this information in order to get an estimate of how much you actually moved. Right, so one way of thinking about it is that it's actually a measurement. Right, it is not really a control. Right? It's actually a measurement. But another way of thinking about it is that you look at this as the effect of the control action, right? It's the effect of the control action that was applied to the robot, and so you use this as a surrogate for the actual control that was given. Okay, so why do we use this? So that's what we are mentioning here, that it's an alternative to using the robot velocities. The main reason that we end up using this is because quite often the actual velocities that are imparted to the robot, right? At least the controller that we want, that we are setting it to give a certain velocity, that need not always get translated into physical movements, right? So there is too much noise in that. Often the more accurate movement estimates are obtained by integrating the motion sensor information, integrated from the measurement information rather than from just the control information. Right, and also many commercial platforms make these kinds of accumulated information available to you to make decisions on. Right, so so while the measurement could still be erroneous, right, it's actually typically more accurate than the velocity for a variety of reasons. So there could be some kind of drift and slippage in the actual operating conditions, right, and but apart from that, velocity models also suffer an additional approximation error, right? So we have some kind of a mathematical model that describes how the velocity maps to the movement, but again there could be mismatches in that as well, right? So well, the odometry information is essentially the motion that actually happens, right, and that kind of allows us to ignore the other errors that come from these modeling problems, right? So technically, like I said earlier, odometry are actually sensor measurement, right? They're not control measurements. And so if I actually want to think of the odometry as measurements itself, right, and I might have to add more to the state variables, right? And therefore, instead of expanding my state dimensions to include things like velocity and so on and so forth, not just the x, y, and theta like we saw earlier. So to avoid including the velocity and other things as part of the state information because of looking at the sensor measurements. So we typically take this odometry as a control signal. I will see in the next couple of slides how this is done. But the odometry is treated like a control signal, and then that allows us to actually define a new kind of motion model that is based on the actual odometry measurements as opposed to the real control that was given, right? And so this is used quite often in many of the current day systems, right? This kind of odometry motion models, right? So the idea here is that we are going to look at the odometry signal as the action, right? So the UT that we talk about would be the odometry measurements that we make, as we will see in the next slide, right? So as before, our goal here when we are trying to build a motion model is to come up with a probability distribution of xt given the previous state xt minus 1 and the control action ut, right? So so if you think of the actual dynamics of the system, right, as taking the robot from a pose xt minus 1 to a pose xt, right, I can think of the odometry as reporting, right, an advance from x bar t minus 1 to x bar t, where the bars, right, x bar t minus 1 and x bar t are actually the measured values of the pose at time t minus 1 and at time t, right? While xt minus 1 and xt are the actual pose at time t minus 1 and time t, x bar t minus 1 and x bar t are the measured pose as measured by the odometry readings at time t minus 1 and at time t, and we will denote these as we did before. So, where xt minus 1 we denoted as x, y and theta, right, and xt we denoted as x bar, y bar and theta bar, right. Likewise, what we will do is for x bar t minus 1, we will denote these readings as x bar, y bar and theta bar, which is basically the x coordinate measured or estimated, right, the x coordinate measured or estimated from the odometry readings at time t minus 1. This is the y coordinate estimated at time t minus 1, and this is the orientation estimated at time t minus 1. And likewise, this is x bar prime is the x coordinate estimated at time t, y coordinate estimated at time t, and the orientation estimated at time t. Okay, so this is basically, this will be our notation. So, while the robot actually moved from xt minus 1 at time t minus 1 to xt at time t, right, the odometry tells us it moved from x bar t minus 1 to x bar t, right, in that time interval, right. So, what is the use of this, right? So, one of the main reasons why this odometry information is useful, right, even if I am not able to do a correct correspondence between the x bar, y bar, theta bar to x, y, theta, this change that I observe in the estimate, right, from x bar theta, x bar t minus 1 to x bar t, right, is similar or very close to the change that actually happened between xt minus 1 to xt. Get it? So, even if x bar t minus 1 and x bar t are erroneous estimates of the poses at t minus 1 and t, right, I could still say that the change from t minus 1 to t is similar for both the estimated quantities and the actual quantities. So, if from the estimated quantity, if I can get the change, right, then I can apply it to the actual xt minus 1 that I have and also find out what xt is. So, this is essentially, this is what allows us to build the probabilistic model for the actual state based on the estimated measurements from the odometry. Okay. Right. So, that is basically what we are saying here, and so the difference is useful, right. So, now the control itself, right, I am going to now represent it by both the x bar t minus 1 and the x bar t. Basically, it is what I really need from the control ut is to figure out what the change was. So, instead of actually computing the change and giving that as the ut, which is the motion information, so I am going to say ut basically consists of two successive estimated poses, which is x bar t minus 1 and x bar t. Okay, that is what my ut is, right. So, what I do now is I transform this the relative odometry information, right, into a sequence of 3 steps, okay, which we will call as delta rotation 1, delta translation and delta rotation 2. Okay, so, what are these, right? So, delta rotation 1 is essentially taking the original orientation of the robot, and moving it so that it faces in the direction of the translation, right. So, I know this, right. So, basically, if this is essentially my x bar t minus 1 and that is my x bar t. Okay. So, what I do is this delta rotation 1 is rotating the robot, the theta bar, so that it now points in the direction of the translation, right. The direction I know from my x bar, y bar and x bar prime, y bar prime, right. So, now it points in the direction of the translation, right. And then I do the delta translation so that I move the robot to the destination location, and I still have a residual angle, right, that I need to model. So, delta rotation 2 basically rotates the robot to the final orientation, which is theta prime, right. This is theta bar prime, this is the final orientation of the robot from the direction of motion. So, I will take the direction of motion and change it to the final orientation. So, I have decomposed my total motion into delta rotation 1 delta translation, and then another delta rotation 2. So, this is essentially how I do it. So, given any pair of positions S bar and S bar prime, which are any two poses, I can basically reduce it into a unique delta rotation 1, delta trans, and delta rotation 2, and for every pair of states I can basically recover this, right. And then what I do is, just as I did in the velocity motion model, I am going to assume that there are independent sources of noise for all the three, and my overall probability is basically given by the product of these three noises. Okay. So, again, while we are constructing this algorithm, that will output the probability. Suppose I give you an initial pose xt minus 1, a control which is ut, in this case which is two sets of measurements xt minus 1 bar and xt bar, and a final pose xt, right. Given this algorithm is going to return the probability of xt happening when I apply ut to xt minus 1. So, what does applying ut mean here? That means that I have done the translation to my state as given by these two vectors. Okay. So, I have my initial pose, which is x, y, theta, right, and then I have the translation, the delta rot 1, right, and delta trans and delta rot 2 as specified by this pair of vectors in ut, that is my action, and then I finally have the successor pose given by x prime, y prime, theta prime, right. What is the probability that this is the successor pose, given that I started with that state, right, and then applied the translation or applied the action as specified by these two measurements. So, that is basically the problem here. So, right now this is how we are going to do this. So, lines 2, 3 and 4, right, lines 2, 3 and 4 actually compute the rotation and the translation differences as per the measured pose, which is ut, right. So, this is basically telling me, okay, how much has the pose changed from x bar t minus 1 to x bar t, okay, that is what 2, 3, 4 tells me. 5, 6, 7 tells me how much the position has changed from xt minus 1 to xt, right, that is what the cap is, okay. Delta cap rot 1 is basically delta rot 1, the same expression as delta rot 1, but computed on the x, y and x bar, y bar, right. Here it is computed on x prime, y prime, sorry. Here it is computed on x bar, y bar and x prime bar and y prime bar and theta bar, while in 5, 6, 7 I actually use the measurements, the states given in xt and xt minus 1, right. Now, once I have done this, basically what lines 8, 9 and 10 do is exactly the same noise model that we had earlier, right. So, now this is a zero mean probability distribution with variance is this. So, I really want my rotation 1 and my rotation 2, rotation 1 delta hat to be the same values, right. So, I basically want my odometer measurements to be accurate. So, if I am assuming the odometer measurements are accurate, then delta rot 1 minus delta cap rot 1 should be 0. So, I will model this noise in the first rotation, right, difference by the factor P1, which basically gives me a sample from a zero mean probability distribution with variance given by alpha 1 rot 1 cap plus alpha 2 delta trans cap, right. So, this means how much I rotate and how much I translate, both of these are going to contribute to the noise in the first rotation. Similarly, both the rotations and the translation errors changes are going to contribute to the error in the translation, and finally, the translation and the second rotation, the magnitude of those is going to contribute to the error in the second rotation that we have. So, each we are assuming as independent sources of error. So, I have P1 times P2 times P3. Okay, very similar to what we had earlier. So, it is not very complicated, except that the control is given by a slightly different way of specifying it, which is the odometry information, and we also get a slightly different noise model. There it was earlier it depended on the magnitude of the velocities, right. The noise that we used was dependent on the magnitude of the translational and the rotational velocities, but now it is going to be at the based on the magnitude of the actual rotation and the actual magnitude of the translation itself. Okay. So this is basically explaining what is happening there. Lines 2 to 4, I get the relative motion parameters from the odometer readings, and lines 5, 6, 7, I get the actual the relative motion parameters from the actual poses that were given, right? And 8 to 10, 8, 9 and 10 compute the error probabilities for the individual motions, and then finally I multiply all of them to give back the overall probability of seeing that actual transition. Okay. And you can see the same setting here like we did with the different alpha settings. So this is again for a normal alpha setting, and you can see that both the angular and the translational spread, because all the alphas are normally spaced, and here is more translational error and lesser angular error, and in C I have more angular error and less translational error, exactly the same kind of parameter settings as we had earlier. So the actual alpha 1 to alpha 6 values might be different, but the settings are similar, right? Notice that the final angular differences might lie between minus pi and plus pi, and therefore we have to make sure that we are truncating everything appropriately, right? And just like we did earlier with the particle filter version of the motion model, we can do a particle filter version of the motion model, where we first compute delta ROT1, delta trans and delta ROT2, and then we sample a delta prime, right? Remember, when I am using the particle filter version, I don't get an xt as an input, right? So I can't compute delta ROT1 because I don't have an xt as input, but what I do is I randomly sample values for the delta cap, right? All the 3 delta cap values I sample randomly, and once I have a sample, and then I do a deterministic computation of what x prime, y prime and theta prime should be based on the cap values I have computed, right? And then that gives me the final sample of the state, and if I repeatedly call this function, I will get many different samples. And just like last time, you can see that again for 500 samples, this looks like a very similar figure to what we saw with the motion model. Okay. So the challenge with using the odometry model is that the odometry information is available to you only after the motion is completed, not before the motion has happened, right? So in the filtering use case that we have seen so far, right, for filtering it is fine because we typically use the motion model only after the actual motion has been completed. But when we are trying to do planning, as we will see later, right, we really need to make predictions before the motion is completed. In such cases, we have to fall back on using something like the velocity motion model, right? So the odometry motion model can be used in cases where the motion has been completed, and we are just using the particle filter for doing the state estimation, right, or the base filters for using state estimation. In such cases, we can use the odometry model because we really need it to complete. So typically, this is something what you would see here. I have applied a particle filter based odometry model here, and you can see that as I keep moving, right, so my estimates become increasingly uncertain, right? This is only based on the motion model, right? I have not incorporated any observations here, right? Once I start incorporating observations, these things will again start relocalizing. But right now, just to give you a feel of what happens when I use the motion model alone to make the predictions as I keep moving, right? The probability distribution keeps spreading out. So I basically started here and I have moved around like that, and you can see that how the noise always keeps increasing, right, until I make a measurement so that I can collapse this uncertainty, right? So just a small note here, we'll come back to maps in greater detail later on, but just to tell you the importance of incorporating map information when I am doing this kind of motion models, and same thing with the measurement models, right? So we have described all the motion so far, assuming that we have no knowledge about the environment, and anything that needs to be captured is somehow captured in the motion model itself. But the motion models that we have looked at are fairly straightforward and simple, right? So they basically look at small linear motion, right? This is a small rotation followed by a translation. It really doesn't talk about anything that's there in the environment itself, right? So in many cases, we typically have some kind of a map, right? The map tells us whatever information that we have about the environment in which the robot is currently moving, right? And so we look at later, there is something called occupancy maps, right? So for example, that tells us whether a particular location or particular pose is free, right? Free meaning that the robot can actually move over that space, or is it occupied? Right? Occupied meaning that could be an obstacle, could be a table, chair, could be some kind of walls or whatever, right? The robot is not able to go over that space. So these kinds of occupancy maps will tell us whether the space is free or not. And so the robot's pose must always be in the free space, right? So knowing the map allows us to further refine our motion model, right? So now our motion model should start looking like this. What is the probability of xt given that I started in xt minus 1, I did action ut, and I am operating in a map m, right? So I'll have to start conditioning my motion models on the map m. And if m carries information relevant to the pose estimation, right? So if m is something that is going to actually affect what I'm estimating, then typically ignoring the pose information is going to give me wrong information, wrong estimates of the pose, right? So it can become arbitrarily complex, right? It can become arbitrarily complex. So what typically we do is, whenever the motion is very small, whenever I'm going to make a very small transition from xt minus 1 to xt, right? So what do I mean by that? That means that I should be making these predictions very frequently, right? I should make the predictions very frequently between, so every pose, right? I shouldn't wait for a large motion to be completed before I make the prediction. In such cases, I can approximate this probability by two things, right? So I can look at the original motion model like I had earlier, which is probability of xt given ut and xt minus 1, and some kind of a validity model, okay? So what is the probability that xt is a valid pose, right, given that I'm operating in a map m, right? So I've moved from xt minus 1 to xt, right? Is xt a valid pose, right? So given that I'm operating in map m, and eta as usual is some kind of a normalizing factor. Right, so this I'm only checking for the validity of the final pose, and as long as the changes are small, right? So this should be fine, right? So the second term, sometimes you can also think of it as a consistency of the pose with respect to the map m, right? For example, in the case of occupancy map, so the probability of xt given m is 0 if the robot collides with an occupied grid. Right? Otherwise, we'll give it some small constant value depending on what the normalization factor is, right? Then this can become your probability estimate, right? So it becomes a very easy case now, right? So if xt given m is, if xt is actually a occupied grid cell in m, then the probability is 0. If xt is not an occupied grid cell, if the map says that xt is free, then it will have some constant value. So it becomes easy. So the computation is not any complex, right? So basically the original motion model, it will either be multiplied by a 0 or by a constant. And the constant could potentially be absorbed into eta. So you can either take it as being multiplied by 0 or multiplied by 1, right? Right. So here is a simple example, and so I take an xt, right, which is the original sample of the motion model, right, and then I look at the probability of xt being valid given m, right. If the probability is greater than 0, right, then this is a valid pose. So I'll return that xt comma pi to my motion model. If my pi is 0, that means that wherever I have moved, right, the sample that I have generated for xt is not a valid pose. This is then, therefore I keep sampling until I get a valid pose, final pose xt, right. So this technique is called rejection sampling, right. So I have a complicated distribution to sample from, but the complication can be broken into two parts, right. I have a simple distribution, which is the motion model, that the simple motion model that I can sample from, right. But then I have certain exclusions. So whenever I hit one of those excluded samples under the model, I just ignore it, I reject it, and I keep drawing more samples, right. So the effective sampling distribution would not be the one given by the motion model itself that we had earlier, but where the probabilities corresponding to these xt's, which have a 0 probability under this distribution have been set to 0. So this is called rejection sampling. It's a very easy way of accounting for this kind of corner rejection cases without making the base sampling distribution more complicated, right? So this will work something like this, right? So my original motion model, let us say, is this gives me a probability distribution as indicated here in this figure, right? And let us say that there is actually an obstacle here, that's a wall or a partition here that I can't occupy, right? So there will be some small region around the partition because my robot has a volume, right? So there is a small region around the partition which the robot can't occupy. So all those states have to become 0 probability. So now, so instead of sampling from this distribution for my next state, I'll be sampling from this distribution. Note that these parts have become actually denser, right? So these have become darker. Therefore, that means the probability mass here is higher than the probability mass here. And so everywhere else, the probability would be 0. Okay. Right. So still there is a problem, right? Look at this region which I have denoted by a star, right? This region, right? Still there is a problem because even though according to the map this is a valid region, for the robot that is standing here, right? For the robot that is standing here, to reach this region, it actually has to go through the obstacle, right? So that is a challenging part, right? So so this is what we are basically saying here. So in the real world that is not possible, right? So if our updates are small, right? If I'm updating very frequently, right? Then this kind of situations are going to very rarely occur in practice, because as soon as I move little bit, right? I can never find myself on the other side of the obstacle, right? I'll find myself in a state where I'm actually hitting the obstacle, therefore I'll not move, right? I'll have to look at a different way of completing the motion, right? It's only because I'm looking at a larger translation here, right? I'm actually having these kinds of infeasible cases. And even in other cases, sometimes we might have to actually check for the entire path if it is collision free, right? So sometimes you have to do a very expensive check to make sure that we are looking at valid translations, right? The valid motions, right? So we have to be very careful about choosing our update frequency for the filter as well, okay?